In August of 2024, the James Webb Space Telescope pointed its most powerful infrared eye at the closest sun-like star to Earth, Alpha Centauri A, just 4 light-years away. When astronomers processed the data and subtracted the blinding glare of the star, something was sitting there in the image. A faint blob of light, over 10,000 times dimmer than the star itself. It looked exactly like what a Saturn-mass gas giant would look like if it were orbiting in the habitable zone of our nearest stellar neighbor. The team tried to debunk their own finding. They checked for instrument artifacts, background galaxies, stray light. Nothing explained it away. So they pointed JWST at the same star again in February 2025 and again in April. Both times, the object was gone. Not destroyed, not disproven, simply absent. The most powerful space telescope ever built found what appears to be a planet next door and then could not find it again. This is the story of the most tantalizing disappearing act in modern astronomy. To understand how that faint smudge of light ended up in the processed data of the most expensive scientific instrument ever launched into space, you need to understand the people who went looking for it, and the almost absurd difficulty of what they were attempting to do. Because pointing the James Webb Space Telescope at Alpha Centauri A was not a routine observation. It was closer to an act of controlled madness, a calculated gamble that required the team to push JWST beyond what it was originally designed to handle, into a regime of brightness and complexity that would make most astronomers walk away before they even submitted the proposal. The team was led by Charles Beekman, a veteran astronomer at NASA's Jet Propulsion Laboratory and the NASA Exoplanet Science Institute at Caltech. Beekman had spent decades working on the science of detecting planets around other stars, not through indirect methods like watching a star dim or wobble, but through the far more brutal approach of direct imaging. Photographing the planet itself, capturing photons that originated not from the star but from the tiny world hiding in its glare. Direct imaging is the rarest and most technically punishing method of finding exoplanets. It requires you to tease out the feeble glow of a tiny cold world from the overwhelming brilliance of the star it orbits, a star that can be thousands or millions of times brighter, separated by an angle so small that both sources blur together into a single smear of light on your detector. Standing alongside Beekman was Aniket Sanghi, a PhD student in astrophysics at Caltech who had been looking for the next great challenge in this field. He wanted the hardest possible target, something that would test the limits of the telescope and the limits of his own skill as a data analyst. Alpha Centauri A turned out to be exactly that. Not because it is faint or distant, the opposite. Alpha Centauri A is the 4th brightest individual star in the night sky. It sits just 4.37 light-years away, making it the closest sun-like star to our solar system. That proximity should make things easier. In almost every other area of astronomy, closer means clearer. But in direct imaging, the overwhelming brightness of a nearby star creates a wall of light that buries everything around it. And Alpha Centauri A does not sit alone. It has a companion. Alpha Centauri B, a slightly smaller and cooler star, orbits alongside it in a gravitational waltz, adding its own flood of photons to an already blinding scene. Any planet hiding near Alpha Centauri A is buried under the combined glare of 2 stars. The weapon the team chose to cut through that glare was MIRI, the mid-infrared instrument aboard JWST. MIRI is one of 4 instruments on the telescope, and it is the only one that sees the universe in the thermal mid-infrared, at wavelengths between 5 and 28 microns. This is a region of the electromagnetic spectrum that is completely invisible to human eyes. It is also largely invisible to telescopes on the ground, because the water vapor in Earth's atmosphere absorbs mid-infrared light before it can reach any detector on the surface. At 15 microns, the wavelength the team chose for their observations, the atmosphere is essentially opaque, You cannot do this kind of science from Chile or Hawaii or the top of any mountain. You have to be above the atmosphere entirely. You have to be in space, and not just anywhere in space. You have to be at the second Lagrange point, 1.5 million kilometers from Earth, where JWST orbits in the cold shadow of its massive sun shield, its instruments chilled to temperatures below 50 Kelvin, cold enough that the telescope's own thermal emission does not blind its own detectors, cold enough to see the faintest whisper of heat from a world 4 light-years away. The reason mid-infrared light is so critical for this search comes down to the physics of temperature and radiation. A gas giant planet like Saturn or Jupiter, sitting at a comfortable distance from a sun-like star, does not reflect much visible light. It is too far from the star, too cold, too dim in the optical spectrum, but it does radiate heat. Every object with a temperature above absolute zero emits thermal radiation, and for a cool gas giant at roughly 200 to 250 Kelvin, that thermal glow peaks in the mid-infrared. At 15 microns, the contrast ratio between the star and the planet drops dramatically. In visible light, a sun-like star outshines a Saturn temperature planet by a factor of roughly 1 billion to 1. At 15 microns, that ratio drops to roughly 10,000 to 1. That is still a staggering difference. If the star were a bonfire, the planet would be a birthday candle held a few feet away. But 10,000 to 1 is the difference between absolutely impossible and maybe, just barely, with the right instrument and the right technique, achievable. But even at these favorable wavelengths, you cannot simply point JWST at a bright star and expect to see a planet sitting next to it. The star's light still dominates. To suppress that light, the team used one of MIRI's built-in coronagraphs. A coronagraph is a device designed to block the light from a star so that faint objects near it can be revealed. The concept dates back to 1930, when the French astronomer Bernard Liot invented the first coronagraph to study the sun's corona without waiting for a total solar eclipse. He placed a small opaque disk inside his telescope to block the solar disk, allowing the faint outer atmosphere of the sun to become visible. The principle is the same today, but the technology has evolved almost beyond recognition. MIRI carries 4 coronagraphic masks. 3 of them are 4-quadrant phase mask coronagraphs, each tuned to a different wavelength. The 4th is a classical Liot-style coronagraph for observations at longer wavelengths around 23 microns. For the Alpha Centauri campaign, the team selected the F1550C configuration, pairing the 4-quadrant phase mask with a filter centered at 15.5 microns. Here is how this device works, and it is genuinely one of the most elegant pieces of optical engineering ever sent into orbit. Picture the focal plane of the telescope, the flat surface where the image of the star is formed. Now imagine dividing that focal plane into 4 equal quadrants, like cutting a square into 4 equal pieces with a vertical and a horizontal line through the center. In 2 of those quadrants, diagonally opposite to each other, the mask introduces a precise half-wave phase shift to the incoming starlight. This means the light waves passing through those 2 quadrants are delayed by exactly half a wavelength compared to the light passing through the other 2 quadrants. When the star is perfectly centered on the intersection of the 4 quadrants, something beautiful and destructive happens. The light from the phase-shifted quadrants and the light from the unshifted quadrants arrive at the detector exactly out of step. Crest meets trough. Peak meets valley. The waves cancel each other out through destructive interference. The starlight is annihilated at the center of the image. Not perfectly, of course. No physical system achieves perfect cancellation. Tiny imperfections in the telescope's optics, microscopic vibrations, thermal fluctuations in the mirror segments, all of these create residual starlight that leaks through the coronagraph. But the suppression is dramatic. A factor of 1,000 or more at the smallest angular separations from the star. Behind the phase mask sits a Lyot stop, a secondary optical element designed to clean up the diffracted light that spills around the edges of the telescope's segmented primary mirror. Together, the phase mask and the Lyot stop carve out a zone of deep shadow in the immediate vicinity of the blocked star. And in that shadow, if the universe is generous, you might find something real. But suppressing Alpha Centauri A was only the first problem. The second was its companion. Even with the coronagraph perfectly centered on Alpha Centauri A, Alpha Centauri B was lurking nearby in the field of view, a blazing intruder pouring scattered and diffracted light across the detector. The contamination from the companion star had to be identified and removed separately. This required a technique called reference differential imaging. The concept is deceptively simple. You observe your target star with the coronagraph in place. Then you slew the telescope to a different star, a reference star with similar brightness and spectral type, and observe it with the identical coronagraphic setup. Because the optical artifacts created by the telescope and the coronagraph depend on the instrument, not on the star, the artifacts should be nearly identical in both images. Subtract one from the other, and the artifacts cancel. What remains is anything unique to the target observation, anything real, like a planet. In practice, this is agonizingly difficult. The reference star has to be close in brightness and color to the target. The telescope has to maintain the same pointing stability and thermal state. The coronagraphic mask has to be centered with the same precision. Any mismatch between the target and reference observations leaves behind subtraction residuals, bright spots and dark spots that can mimic or hide a real signal. The team had to perform this subtraction not just for Alpha Centauri A, but also for the contaminating light from Alpha Centauri B, effectively doing double coronagraphy on a single complex field. And there was yet another complication. The standard procedure for placing a star behind a coronagraphic mask involves the telescope's target acquisition system, which locks onto the star and centers it with extreme precision behind the mask. But this procedure struggles when there are two very bright stars sitting close together in the same field. The guidance sensors can become confused, locking onto the wrong star or splitting the difference between the two. So the team devised a workaround that borders on the ingenious. They used a third star, Epsilon Muscae, as a blind offset reference. They commanded JWST to acquire and lock onto Epsilon Muscae first, then execute a precise slew of a known angular distance to place Alpha Centauri A behind the coronagraphic mask. It was like navigating to a hidden destination, not by looking at the destination itself, but by starting from a known landmark and walking a measured number of steps in a specific direction. This required the telescope's pointing system to be accurate to within a few milliarc seconds, a level of precision equivalent to tracking the width of a human hair from 10 kilometers away. The fact that it worked is a quiet testament to the engineering teams that built and calibrated JWST. The observations were executed in August of 2024. Data flowed from the telescope across 1.5 million kilometers of vacuum through the antennas of the Deep Space Network and into the computers of the research team. The raw images were, predictably, a mess. Residual starlight bled through the coronagraph in complex patterns. Diffraction spikes radiated outward from the positions of both stars. The boundaries between the four quadrants of the phase mask created characteristic cross-shaped artifacts. Hot pixels sparkled randomly across the detector. Optical ghosts, faint secondary images of the stars caused by internal reflections in the optics, drifted across the field. To an untrained eye, the raw data would have looked like a smeared, chaotic fingerprint of light with no discernible structure. But this is where the skill of the team came into play. They ran their data reduction pipeline, a sophisticated sequence of computational steps designed to peel away the layers of noise one by one. They subtracted the reference star observations. They modeled and removed the scattered light from Alpha Centauri B. They corrected for known detector artifacts and flat field variations. They perform the subtraction at multiple telescope roll angles, a technique where the telescope is rotated slightly between exposures so that real astronomical sources move on the detector while instrumental artifacts remain fixed. This allows you to distinguish the two. And when they were finished, when every known source of contamination had been stripped away, a faint point source was sitting in the processed image. It was located at a projected separation of roughly 2 astronomical units from Alpha Centauri A. Its brightness in the mid-infrared was consistent with a gas giant planet roughly the mass of Saturn, at a temperature of around 200 to 250 Kelvin. It was over 10,000 times fainter than the star. The team designated it S1. Sanghi recalled the moment with the careful understatement that marks a scientist who has spent enough time chasing ghosts to know the difference between hope and evidence. "You are very skeptical of anything you see," he said, "but this one just popped out so clearly. The signal was not ambiguous. It was not a vague smear requiring statistical arguments to justify its existence. It was a point source, compact and distinct, sitting exactly where a cool gas giant would sit if one happened to be orbiting in the habitable zone of Alpha Centauri A." But Sanghi and Beischmann knew the rules of this game. In direct imaging, the universe is a master forger. Instrumental artifacts can masquerade as planets. Detector glitches can mimic point sources. Scattered light from the coronagraph can create phantom blobs in exactly the wrong place. So the team did what any responsible group of scientists would do. They tried to destroy their own result. Could S1 be a background galaxy? Distant galaxies emit thermal radiation in the mid-infrared and can appear as point sources at JWST's resolution. The team checked. No known background object was catalogued at that position. And because Alpha Centauri moves rapidly across the sky due to its proximity, roughly 3.7 arcseconds per year, a fixed background galaxy would shift in apparent position relative to the star over time. S1 appeared firmly associated with Alpha Centauri A. Could it be a foreground asteroid drifting through the field of view? Asteroids are warm and glow in the infrared, but they move visibly across the sky over the timescale of an observation. S1 did not trail across the detector. It remained stationary relative to the star. Could it be an optical ghost, an internal reflection within the telescope's complex optical train? MIRI has well-documented ghost patterns, and the team had mapped them thoroughly. S1 did not correspond to any known ghost. Could it be a residual of the PSF subtraction, a bright spot left behind by imperfect cancellation of the starlight? The team tested this by injecting fake planet signals into the raw data at known positions and brightnesses, then running them through the same reduction pipeline. Their pipeline recovered the fake planets accurately and did not produce false signals at the position of S1. The detection was robust. Nothing the team threw at S1 could make it go away. Every alternative explanation crumbled under scrutiny. And then the story took a turn that transformed it from an exciting single detection into something altogether more extraordinary. Because the JWST team was not the first group to see a suspicious signal near Alpha Centauri A. 5 years earlier, in 2019, a different team, using a different telescope on the ground, had found something strikingly similar. That earlier observation was part of a project called NEAR, an acronym for New Earths in the Alpha Centauri region. It was a collaboration between the European Southern Observatory and Breakthrough Watch, a privately funded program dedicated to searching for habitable planets around nearby stars. The NEAR team had upgraded the Very Large Telescope in Chile's Atacama Desert with a custom thermal infrared coronagraph, specifically designed and optimized for the Alpha Centauri system. Over a month in May and June of 2019, they accumulated nearly 100 hours of observation time on Alpha Centauri, collecting more than 5 million individual images and approximately 7 terabytes of data. When they processed that enormous dataset, subtracting instrumental artifacts and stellar residuals, they found a faint, point-like source in the habitable zone of Alpha Centauri A. It was located at a projected separation of approximately 1.1 astronomical units from the star. They designated it C1, Candidate 1. The brightness was consistent with a planet somewhere between the size of Neptune and Saturn. There was even a hint of elongation in the source, as though the planet had moved slightly during the 19-day observing window, exactly as you would expect for an object on an orbital path. The result was published in Nature Communications in February of 2021, but the team was cautious. They stated clearly that without independent verification, an instrumental artifact of unknown origin could not be ruled out. C1 had entered the scientific record not as a confirmed planet, but as an open question. Now, 5 years later, JWST had found S1 at a different position, roughly 2 astronomical units from the star. The two detections were separated in time by 5 years and in apparent position by about 1 astronomical unit. But this was not a contradiction. It was potentially a confirmation. If S1 and C1 were the same object, a planet on an elliptical orbit, then the difference in position was exactly what you would expect. In 2019, the planet would have been closer to the star, near the inner portion of its orbit. By 2024, it would have swung outward toward the more distant part. 2 snapshots of the same world, captured at different moments in its journey around the star. The team explored this hypothesis with rigorous orbital modeling. They combined the positional data from both detections and used them as anchor points for orbit fitting, running millions of simulated orbits through their models. They constrained these simulations by requiring that any viable orbit be gravitationally stable in the presence of Alpha Centauri B, whose gravitational influence carves out regions of instability that would eject a planet from the system entirely. The results converged on a compelling picture. The data were consistent with a gas giant, roughly the mass of Saturn, between 90 and 150 Earth masses, approximately the size of Jupiter in radius, traveling around Alpha Centauri A on an elliptical orbit. The planet's distance from the star would vary between roughly 1 and 2 astronomical units. The orbital period would fall somewhere between 2 and 3 years. The eccentricity, the degree of orbital elongation, was estimated at around 0.4. It was not a circular path. It was an oval, a stretched loop that carried the planet alternately closer to and farther from its star with each revolution. If this was real, the implications were staggering. Sanghi laid them out with precision. Of all the directly imaged planets, this would be the closest to its star seen so far. It would also be the most similar in temperature and age to the giant planets in our own solar system. And it would be the nearest such planet to Earth. Its very existence in a system of 2 closely separated stars would challenge our understanding of how planets form, survive, and evolve in chaotic gravitational environments. Beischmann put the stakes in even broader terms. With this system being so close to us, any exoplanets found would offer our best opportunity to collect data on planetary systems other than our own. But for all the excitement, one word hung over everything like a shadow. If confirmed, if real, if the signal was not an artifact too subtle for the team to identify, the astronomical community would not accept a single epoch of JWST data and a 5-year-old ground-based hint as proof of a planet. The standard for confirmation is clear and unforgiving. You need multiple independent detections, ideally at different orbital positions, demonstrating that the object moves in a manner consistent with a gravitationally bound orbit around the star. One observation is a hint. 2 observations from different instruments are intriguing. 3 or more with measured orbital motion is a discovery. The team needed to go back. They applied for director's discretionary time on JWST, a special allocation of telescope hours reserved for observations that are scientifically urgent and cannot wait for the standard annual proposal cycle. The request was approved. In February of 2025, JWST turned once more toward Alpha Centauri A. The same instrument, the same coronagraphic mask, the same wavelength, the same painstaking observation strategy. The data were collected, downlinked, and processed through the same pipeline. The planet was not there. They tried again in April of 2025. Same setup, same extraordinary sensitivity, same care. Nothing. The region of the image where S1 had appeared 7 months earlier was clean, empty, silent. 2 follow-up attempts with the most sensitive mid-infrared observatory in existence, and the candidate had vanished from the data. It was as if someone had opened a door into a room, seen a figure standing in the corner, closed the door, opened it again, and found the room empty. Twice. The figure had not walked out. There was no exit. The room was sealed, and yet the corner was bare. Sanghi captured the mood of the moment in a single sentence that would soon travel around the world. We are faced with the case of a disappearing planet. It was a line that balanced wonder against frustration, playfulness against genuine scientific gravity. Because the disappearance was not the end of the story. It was, in many ways, the true beginning. The absence of the signal in early 2025 was not a refutation. It was a puzzle. And it was a puzzle whose answer, when the team sat down with their orbital models and their understanding of how coronagraphs actually work, turned out to be hiding in plain sight. The planet had not vanished. It had moved. And where it had moved to was exactly the one place where even the James Webb Space Telescope could not follow. The human brain is wired to interpret absence as negation. If you open a drawer and the keys are not there, you conclude the keys are somewhere else. If you look for a friend in a crowd and do not see them, you assume they left. Absence feels like an answer. It feels like closure. But in astronomy, absence is almost never an answer. It is a constraint. It narrows the possibilities without eliminating them. And in the case of the disappearing planet candidate around Alpha Centauri A, the absence in the February and April 2025 observations was not a verdict of non-existence. It was a piece of orbital mechanics hiding in the mathematics of how coronagraphs work. To understand why the planet vanished from the data, you have to understand a concept that sits at the heart of every coronagraphic observation ever performed. It is called the inner working angle. Every coronagraph, no matter how sophisticated, has a blind spot. There is a minimum angular distance from the blocked star below, which the coronagraph simply cannot suppress enough light to reveal a faint companion. Inside that boundary, the residual starlight is still too bright, too structured, too chaotic for any data processing pipeline to extract a planetary signal. The inner working angle of MIRI's 4-quadrant phase mask at 15.5 microns is roughly 1 times the ratio of the wavelength to the diameter of the telescope's primary mirror, which translates to an angular separation of approximately 0.49 arcseconds on the sky. For Alpha Centauri A at a distance of 4.37 light-years, that angular limit corresponds to a physical separation of roughly 1 astronomical unit. Anything closer to the star than about 1 astronomical unit is effectively invisible to the coronagraph. It is swallowed by the residual glare. Now think about what the orbital models were telling the team. The planet candidate, if real, was not on a circular orbit. It was on an elliptical one, with an eccentricity of roughly 0.4. That means its distance from Alpha Centauri varied significantly over the course of each orbit. At its farthest point, the planet would swing out to roughly 2 astronomical units, well beyond the inner working angle, clearly visible in the coronagraphic shadow. This is presumably where it was in August of 2024, when S1 appeared in the data. But at its closest approach to the star, the planet would dip inward to roughly 1 astronomical unit, or even slightly less, crossing the inner working angle and plunging into the zone where the coronagraph cannot see. The team ran the numbers. They took their millions of simulated orbits, the ones that fit both the S1 detection from 2024 and the C1 detection from 2019, and asked a simple question. For each of these orbits, where would the planet have been in February and April of 2025? The answer was striking. In 52% of the viable stable orbits, the planet would have moved close enough to Alpha Centauri A during both of those follow-up windows to fall inside the coronagraph's inner working angle. It would have been there. It would have been real. It would have been orbiting exactly as a planet should, but it would have been hiding behind the curtain of residual starlight in the one place where even the James Webb Space Telescope is blind. This is a profoundly important distinction. The non-detection did not mean the planet was absent from the system. It meant the planet was absent from the part of the system that JWST could see at that particular moment. Imagine you are standing in a park at night with a powerful flashlight. You sweep the beam across the grass and you see a rabbit sitting 30 feet away. You look down at your phone for a moment. You look back up and sweep the beam again. The rabbit is gone. Did the rabbit cease to exist? Did you hallucinate it the first time? Or did the rabbit simply hop behind a tree into the one shadow your flashlight cannot reach? The coronagraph's inner working angle is the tree. The planet hopped behind it. Sanghi explained this with characteristic precision. We found that in half of the possible orbits simulated, the planet moved too close to the star and would not have been visible to Webb in both February and April 2025. That sentence, buried in the technical discussion of the research papers, is the key that unlocks the entire mystery. The disappearance was not evidence against the planet. It was consistent with the planet being exactly where it should be on an elliptical orbit, temporarily tucked inside the glare of the star, waiting for its orbit to carry it back out into the observable zone. But consistency is not confirmation, and the team was careful to say so. Having 52% of your orbital models explain the non-detection is encouraging. It means the disappearance does not require any exotic or unlikely explanation. But it also means that 48% of the viable orbits would have placed the planet in a position where it should have been visible in the follow-up observations. If it was real and on one of those orbits, why did they not see it? The answer could be noise. The February 2025 observations were compromised. They suffered from a technical setback that degraded their sensitivity. The team had planned to observe Alpha Centauri A at 2 different telescope roll angles, a standard technique in coronagraphy that allows you to separate real sources from instrumental artifacts by their behavior as the telescope rotates. But only one of the 2 planned rolls was successfully executed. On top of that, there was a position mismatch of approximately 10 milliarc seconds between Alpha Centauri A and the best matching reference star observation behind the coronagraphic mask. 10 milliarc seconds is tiny. It is roughly the angle subtended by a coin viewed from 200 kilometers away. But in high contrast coronagraphy, where you are trying to detect signals 10,000 times fainter than the residual starlight, even a 10 milliarc second misalignment introduces subtraction residuals that can mask or mimic faint sources. The February data were usable but compromised. They set upper limits on the presence of a planet, but those limits were not as deep as the team had hoped. The April observations fared better in terms of execution, but the planet was still not detected. This could mean the planet was genuinely inside the inner working angle during both epochs. It could mean the planet does not exist, and the August 2024 detection was an artifact too subtle for the team to identify. Or it could mean something in between, a real signal at the edge of detectability that the follow-up observations were not quite sensitive enough to recover. Exoplanet science lives in this grey zone. The line between a detection and a non-detection is not a sharp cliff. It is a foggy slope where signal and noise blend into each other, where the same photons can be interpreted as evidence for a planet or as a statistical fluctuation depending on the assumptions you bring to the analysis. This is why the team did not declare defeat, and it is why they did not declare victory. They did something far more scientifically honest. They presented all the data, the detection and the non-detections, laid out the orbital models, identified the range of possibilities, and invited the community to scrutinize every step. The 2 research papers, accepted for publication in the Astrophysical Journal Letters, constitute not a discovery announcement but a status report. Here is what we saw. Here is what we did not see. Here is what the models say. Here is what we need to do next. What they need to do next is wait. And that waiting is not idle. It is strategic. If the planet candidate is real, and if the combined S1 and C1 detections trace the same object on an orbit with a period of roughly 2 to 3 years, then the planet's position relative to Alpha Centauri A changes continuously. There will be windows of time when the planet is far enough from the star to be detectable by JWST's coronagraph, and windows when it dips too close and disappears behind the inner working angle. The team calculated that the next favorable observing window, when the planet should again be at or near its maximum separation from the star, would occur around August of 2026. That is roughly 2 years after the original detection, consistent with 1 full orbital period. If the planet is there, and if it has swung back out to its farthest point, JWST should be able to see it again. The team is working to secure telescope time for that crucial observation. If they point MIRI at Alpha Centauri A in August of 2026 and see S1 again, at a position consistent with the predicted orbit, the case for a real planet will become enormously stronger. It would mean 3 independent detections across 3 different telescopes and 3 different epochs: 2019 with VLT, 2024 with JWST, and 2026 with JWST. Again, all consistent with a single object on a gravitationally stable elliptical orbit. That would not yet constitute a formal confirmation by the strictest standards of the International Astronomical Union, but it would push the probability far beyond what any reasonable skeptic could dismiss. If they look in August 2026 and see nothing, the situation becomes more complicated. It could mean the planet is on a longer period orbit than expected and has not yet returned to maximum separation. It could mean the 2024 detection was a one-time artifact after all. It could mean the planet exists, but its orbit is more complex than the models assumed, perhaps perturbed by gravitational interactions with Alpha Centauri B in ways the simulations did not fully capture. A non-detection in 2026 would not be fatal to the hypothesis, but it would significantly weaken it. The uncertainty would linger. This is the reality of frontier observational science. It does not deliver clean, dramatic revelations. It delivers hints and constraints and probability distributions. It delivers data that you argue about for years. The history of exoplanet science is littered with candidates that turned out to be real and candidates that turned out to be ghosts. The first claimed detection of an exoplanet around a sun-like star, a planet orbiting Gamma Cephei, announced in 1988, was retracted in 1992 due to concerns about the data analysis, and then reconfirmed in 2003 when better measurements vindicated the original claim. The planet was real all along. It just took 15 years to prove it. The discovery of Proxima Centauri B, a potentially habitable world orbiting the nearest star to our Sun, was announced in 2016 based on radial velocity data. It was immediately questioned by some researchers who worried that stellar activity could mimic the planetary signal. Subsequent observations by multiple independent teams eventually confirmed the planet's existence. but the path from detection to confirmation was not a straight line. It was a winding road full of setbacks, reanalyses, and heated debates at scientific conferences. The Alpha Centauri, a candidate, is walking that same road, and the road is made longer and harder by the specific challenges of direct imaging. With radial velocity detections, you can observe the star hundreds or thousands of times over many years, building up a statistical case for a periodic signal that is almost impossible to fake. With transit detections, you can watch the star dim at regular intervals, each dimming event reinforcing the others. But with direct imaging, each observation is expensive. It requires hours of precious telescope time, elaborate coronagraphic setups, and exhaustive data processing. You cannot simply observe Alpha Centauri A every night for a year and build up a phase curve. Each epoch is a single snapshot, and the gaps between snapshots are measured in months or years. This means the orbital coverage is sparse. The planet is seen at one point in its orbit, then not seen, then hopefully seen again at a different point. Reconstructing the full orbit from these scattered data points is like trying to reconstruct a melody from hearing 3 random notes played years apart. There is another layer of difficulty that makes this particular case almost uniquely challenging. Most directly imaged exoplanets discovered to date orbit very far from their host stars, at separations of tens or even hundreds of astronomical units. These are typically young, hot, massive planets, still glowing with the residual heat of their formation, orbiting young stars where the contrast between star and planet is less extreme. The poster child for direct imaging is the HR 8799 system, where 4 giant planets orbit at separations of roughly 15 to 70 astronomical units from a young, nearby A-type star. These planets are bright in the near-infrared and far enough from their star that coronagraphic suppression is relatively straightforward. The Alpha Centauri A candidate is a completely different beast. It sits at only 1 to 2 astronomical units from its star. That is deep inside the territory where the star's residual glare is at its worst, right at the edge of the coronagraph's inner working angle. It orbits not a young, nearby star, but an old, mature, sun-like star whose planets have long since cooled from the heat of formation. Its thermal emission is faint, not the roaring infrared glow of a young hot Jupiter, but the quiet warmth of a middle-aged gas giant slowly radiating away its internal heat. Everything about this target makes it harder. The separation is smaller, the contrast is worse, the planet is dimmer, the star is brighter, the binary companion adds noise, and the planet's elliptical orbit carries it periodically into the one place the telescope cannot see. This difficulty is precisely why the detection, if real, would be so scientifically transformative. The team noted that the planet appeared somewhat brighter in the mid-infrared than standard atmospheric models predicted for a Saturn-mass gas giant of this age and temperature. There are several possible explanations for this excess brightness, and each one is scientifically interesting. The simplest explanation is that the mid-infrared photometry is picking up not just the planet but also a contribution from zodiacal dust, a warm ring or disk of dust grains orbiting in the planet's vicinity, similar to the interplanetary dust that fills our own solar system and creates the faint glow known as the zodiacal light. If the Alpha Centauri A system has its own zodiacal dust, it would emit in the mid-infrared and could add to the apparent brightness of a planet embedded within it. This would not be a problem for the detection. It would actually be an additional discovery. Zodiacal dust around a nearby sun-like star would tell us something about the system's architecture and its history of collisions among asteroids and comets. Another possibility is that the planet is rotating rapidly. A gas giant spinning quickly on its axis would be ablate, flattened at the poles and bulging at the equator. If viewed from a favorable angle, a rapidly rotating planet could present a larger apparent surface area to the observer, increasing its thermal emission and making it appear brighter than a slowly rotating planet of the same mass and temperature. And then there is the most evocative possibility. The planet might have rings. Saturn's rings are one of the most iconic features of our own solar system, vast sheets of ice and rock orbiting the planet in a thin disk. Rings reflect starlight and emit thermal radiation. A ring system around the Alpha Centauri. A candidate could increase its apparent brightness in exactly the way the observations suggest. The idea that the nearest planet to our solar system, orbiting a sun-like star, might have its own ring system is the kind of detail that transforms a data point into a world. But all of these explanations are speculative. They depend on the planet being real, and the planet being real depends on seeing it again. Eric Agol, an astrophysicist at the University of Washington who was not involved in the study, offered a perspective that captures the cautious optimism of the broader community. He commended the team's rigorous work, but emphasized that it is too early to call the object a planet. "I have seen planet candidates come and go," he said. But he also acknowledged the extraordinary potential. "If validated," he said, "this is the best case we have for detecting and characterizing a habitable zone exoplanet around sun-like stars in our entire galaxy." That sentence deserves to be repeated. The best case in our entire galaxy. Not because the galaxy lacks habitable zone planets. There are almost certainly billions of them. But because Alpha Centauri A is so close, so bright, so similar to our own sun, and so accessible to our telescopes that a confirmed planet there would be studied more intensely and more productively than any other exoplanet in the sky. It would become a laboratory, a touchstone, a Rosetta Stone for comparative planetology. Beischmann used exactly that language. This would become a touchstone object for exoplanet science, he said, with multiple opportunities for detailed characterization by Webb and other observatories. He was not exaggerating. A confirmed gas giant at 1 to 2 astronomical units from Alpha Centauri A would be observable at multiple wavelengths across the infrared spectrum. Its atmospheric composition could be probed for molecules like methane, ammonia, water vapor, and carbon dioxide. Its temperature structure could be modeled. Its orbit could be refined with exquisite precision over multiple years of monitoring. And the very fact of its existence would tell us something profound about the history and dynamics of the Alpha Centauri system, the closest stellar environment beyond our own. But all of that is contingent on a single thing. The planet has to come back. It has to emerge from behind the curtain of the coronagraph's inner working angle and show itself again in a future observation. The team believes this will happen in August of 2026. They have done the orbital math. They have identified the window. They know where to look and when to look. The only question is whether JWST will be pointed at Alpha Centauri A at the right moment, and whether the signal that popped out so clearly in August of 2024 will appear once more in the shadow of the coronagraph. Until then, the planet candidate exists in a state that would make a quantum physicist smile. It is not confirmed, and it is not refuted. It is not alive, and it is not dead. It sits in a probabilistic limbo, a Schrodinger's planet, real in the models and absent in the recent data, defined not by certainty, but by the boundaries of what we can and cannot see. The team published their results, both the detection and the non-detections, with the transparency that good science demands. They did not oversell the finding. They did not hide the failures. They laid out the full messy reality of a discovery in progress and asked the community to help them figure out what is true. And the community responded with the mixture of excitement and skepticism that has always driven astronomy forward. Because behind all the technical details, behind the coronagraphs and the PSF subtractions and the orbital simulations, behind the jargon and the error bars and the telescope time proposals, there is a question so simple and so ancient that it predates science itself. Is there a world next door? Are we alone in this corner of the galaxy? Or is there a planet orbiting the nearest sun-like star, a planet with rings perhaps, swinging through the habitable zone on a long elliptical path, waiting for us to look at the right moment? The answer is hiding in the orbit. The orbit is hiding in the glare, and the glare is hiding behind a mask the size of a fingernail, mounted inside a telescope floating in the darkness 1.5 million kilometers from home. The next chapter of this story will be written not in words but in photons, captured in the shadow of a star, in August of 2026. The planet, if it exists, is not gone. It is simply waiting. And so are we. We have spent a great deal of time talking about a faint blob of infrared light in a processed telescope image. We have talked about coronagraphs and orbital mechanics and inner working angles. We have talked about detection and non-detection and the agonizing space between the two. But now it is time to step back, way back, because to truly grasp why this particular smudge of light has sent shockwaves through the astronomical community, you need to understand the star it was found next to. Not just as a data point, not just as a bright source that needed to be blocked, but as what it actually is, the nearest sun-like star in the entire cosmos. A twin of the furnace that keeps you alive, sitting so close in galactic terms that light leaving its surface right now would arrive at your eyes before your next presidential election. Alpha Centauri A is not just another star, it is the star. And its story, its structure, its maddeningly complicated neighborhood is what makes the search for planets around it both the most important and most difficult quest in all of modern exoplanet science. Start with distance, because distance is everything in astronomy. Alpha Centauri sits 4.37 light-years from our Sun. That number rolls off the tongue so easily that it is worth pausing to understand what it actually means. A light-year is the distance that light, traveling at roughly 300,000 kilometers per second, covers in one full year. That is approximately 9.46 trillion kilometers. Multiply that by 4.37 and you get the distance to Alpha Centauri, roughly 41 trillion kilometers. In human terms, that is incomprehensibly far. If you launched a spacecraft today at the speed of the fastest probe we have ever built, the Parker Solar Probe, which at its peak velocity screams through space at roughly 692,000 kilometers per hour, it would take you over 6,000 years to arrive. You would launch before the pyramids of Egypt were built and arrive long after every civilization on Earth had risen and fallen multiple times. And yet, in galactic terms, Alpha Centauri is right next door. The Milky Way galaxy is roughly 100,000 light-years across. It contains somewhere between 100 billion and 400 billion stars. Most of them are thousands or tens of thousands of light-years away. The nearest large galaxy, Andromeda, is 2.5 million light-years distant. Against this backdrop, 4.37 light-years is nothing. It is the width of a single blade of grass in a football field. Alpha Centauri is so close that it is practically leaning over the fence. This proximity has enormous scientific consequences. The closer a star is, the easier it is to study anything orbiting it. Angular resolution, the ability to distinguish two closely separated objects in the sky, improves dramatically with proximity. A planet orbiting at 2 astronomical units from a star 4 light-years away subtends a much larger angle on the sky than the same planet at the same separation from a star 40 light-years away. This means the coronagraph does not have to suppress starlight quite as aggressively. It means the planet's thermal emission arrives at the telescope with more photons per second, reducing the integration time needed for a detection. It means that any confirmed planet can be studied in far greater detail than one orbiting a more distant star. Spectroscopy, The technique of spreading a planet's light into its component wavelengths to identify molecules in its atmosphere becomes vastly more feasible when the planet is close enough to deliver a reasonable number of photons. In short, a planet orbiting Alpha Centauri A would be the single most accessible exoplanet target in the entire sky. It would be studied by every major telescope on Earth and in space for decades. It would become the gold standard for comparative planetology, the reference point against which every other exoplanet observation is measured. This is why the stakes around the S1 candidate are so extraordinarily high. It is not just another planet candidate. It is a planet candidate around the one star where confirmation would transform the field. But Alpha Centauri is not a single star. It is a system, and the architecture of that system is both fascinating and infuriating for planet hunters. At the heart of the system are two stars locked in a gravitational embrace. Alpha Centauri A is a G2V main sequence star, a classification that means it is almost identical to our own Sun. It has roughly 1.1 solar masses, a surface temperature of approximately 5,790 Kelvin, and a luminosity about 1.5 times that of the Sun. Its age is estimated at 4.85 billion years, making it almost exactly the same age as our solar system. If you could magically swap Alpha Centauri A into the position of our Sun, you would notice very little difference. The habitable zone, the range of distances where liquid water could exist on a planetary surface, would shift slightly outward due to the higher luminosity, but the overall character of the system would be remarkably similar. Alpha Centauri A is, for all practical purposes, a solar twin. Alpha Centauri B is its slightly smaller companion. It is a K1V star, cooler and dimmer than Alpha Centauri A, with roughly 0.9 solar masses, a surface temperature of around 5,260 Kelvin, and a luminosity about half that of the Sun. It is still a perfectly respectable star by any measure. If it were on its own, it would be a prime target for planet searches, but it is not on its own. It is locked in orbit with Alpha Centauri A. The two stars orbit their common center of mass with a period of approximately 79.9 years. Their orbit is moderately elliptical, with an eccentricity of roughly 0.52. This means the distance between them varies dramatically over the course of each orbit. At their closest approach, called periastron, the two stars are separated by approximately 11.2 astronomical units. That is roughly the distance from the Sun to Saturn. At their farthest point, apastron, they are separated by about 36 astronomical units, slightly closer than the Sun to Pluto. Right now, the two stars are in a phase of their orbit where they are gradually separating, which is actually favorable for planet hunting observations, because the farther apart they are, the less Alpha Centauri B contaminates the field of view around Alpha Centauri A. There is a third member of the system, Proxima Centauri, a tiny red dwarf star of spectral type M5, 5V, with only about 12% of the Sun's mass and a luminosity of roughly 0.17% of solar. Proxima is the closest star to Earth, slightly closer than Alpha Centauri A and B at a distance of about 4.24 light-years. It orbits the central binary at an enormous distance, roughly 13,000 astronomical units, with an orbital period that may exceed 500,000 years. It is so far from the central pair that some astronomers have debated whether it is truly gravitationally bound to them at all, though recent kinematic data suggest it is. Proxima Centauri has its own claim to fame in the exoplanet world. It hosts at least 2 confirmed planets. Proxima b, discovered in 2016 using the radial velocity method, is a roughly Earth-mass world orbiting in the habitable zone of the red dwarf with an orbital period of approximately 11.2 days. Proxima d, a sub-Earth mass planet on a 5-day orbit, was first reported as a candidate in 2022 and independently confirmed in 2025 by the NERP spectrograph. There was also a candidate signal, Proxima C, a possible super-Earth or mini-Neptune on a wider orbit. But the same NERP's observations that confirmed Proxima D were unable to recover the signal, and the planet's existence is now considered unlikely. The discovery of planets around Proxima Centauri was a landmark moment. It proved that the nearest stellar system to our Sun harbors worlds. But Proxima is a red dwarf, a fundamentally different kind of star from our Sun. Red dwarfs are prone to violent stellar flares that can strip the atmospheres of close-orbiting planets. Their habitable zones are so close to the star that planets there are likely tidally locked, with one hemisphere permanently facing the star and the other in eternal darkness. The relevance of Proxima's planets to the question of habitability, as we understand it, is uncertain at best. Alpha Centauri A is a different story entirely. It is a solar twin. If a planet orbits in its habitable zone, that planet experiences an environment remarkably similar to what Earth experiences around our own Sun. The stellar radiation would be similar in spectrum and intensity. The habitable zone would be at a similar distance. The star's age means the system has had billions of years for geological and potentially biological processes to unfold. Finding a planet around Alpha Centauri A is not just finding another world. It is finding a world in conditions that mirror our own with eerie precision. This is why astronomers have been trying for decades, and this is why they have been failing for decades. The fundamental problem is the binary. Alpha Centauri A and B are two bright stars orbiting each other at separations that are, by astronomical standards, uncomfortably close. Their gravitational interaction creates several overlapping challenges that make planet detection extraordinarily difficult, regardless of the method you use. Start with the radial velocity technique, the workhorse method that has discovered the majority of confirmed exoplanets. Radial velocity works by measuring the tiny Doppler shift in a star's light caused by the gravitational tug of an orbiting planet. As the planet orbits, it pulls the star slightly toward and away from the observer, causing the star's spectral lines to shift back and forth by a minuscule amount. For a Jupiter-mass planet orbiting at 1 astronomical unit from a Sun-like star, this shift corresponds to a stellar velocity change of roughly 12 meters per second. For a Saturn-mass planet at the same distance, the shift is smaller, roughly 3 to 4 meters per second. Modern spectrographs can measure radial velocity changes of less than 1 meter per second, which in principle should be more than sufficient. But Alpha Centauri A has a companion. Alpha Centauri B exerts a massive gravitational pull on Alpha Centauri A, causing it to orbit the common center of mass with radial velocity, variations of many kilometers per second over the 79-year orbital period. This enormous signal has to be modeled and subtracted before you can look for the tiny signal of a planet. The binary orbital model is well constrained, but not perfectly. Small uncertainties in the binary orbit parameters propagate into the residuals after subtraction, creating systematic noise at levels that can mask or mimic the signal of a planetary companion. Additionally, Alpha Centauri A is a solar-type star, which means it has its own intrinsic activity. Star spots, convective motions in the stellar atmosphere, magnetic cycles analogous to our Sun's 11-year cycle, all of these produce radial velocity variations that are comparable in amplitude to the signal of a Saturn-mass planet. Disentangling the planet's signal from the binary signal from the star's own noise is a fiendishly difficult data analysis problem. Multiple radial velocity campaigns have been conducted on Alpha Centauri over the years, and while some have reported tentative signals, none has produced a confirmed detection of a planet around either A or B. Transit photometry, the technique that has discovered the most exoplanets thanks to NASA's Kepler and TESS missions, is equally problematic. A transit occurs when a planet crosses the face of its star, as seen from Earth. causing a tiny dimming of the star's light. The probability of a geometric alignment that produces an observable transit decreases with increasing orbital distance. For a planet at 1 to 2 astronomical units from Alpha Centauri A, the transit probability is well under 1%. You would have to be extraordinarily lucky for the orbital plane to be tilted just right. And even if it were, the transit depth for a Saturn-sized planet crossing a Sun-like star would be roughly 1%, easily detectable in principle. But the binary companion introduces photometric contamination that complicates the measurement. No transit of an exoplanet around Alpha Centauri A has ever been observed. Astrometry, the technique of measuring a star's positional wobble on the sky caused by an orbiting planet, faces its own challenges. The European Space Agency's Gaia mission has been mapping the positions and motions of over 1 billion stars with unprecedented precision. In principle, Gaia could detect the astrometric wobble caused by a massive planet orbiting Alpha Centauri A. But the binary adds enormous astrometric motion that must be subtracted, and Alpha Centauri is so bright that it saturates Gaia's detectors, complicating the measurements. Astrometric constraints on planets in the Alpha Centauri system are improving, but they have not yet yielded a confirmed detection. This left direct imaging as the remaining path, and direct imaging of Alpha Centauri A, as we have already seen, is an exercise in masochism. The star is blindingly bright. The binary companion litters the field with scattered light. The coronagraph's inner working angle limits how close to the star you can probe. The planet, if it exists, is old and cold, emitting faintly in the thermal infrared rather than blazing in the near-infrared like the young hot Jupiters that dominate the direct imaging census. Every aspect of the problem is stacked against the observer, and yet, we have already seen why the mid-infrared is the critical wavelength for this search. The spectral range where a cool gas giant's thermal emission is strongest and the star-to-planet contrast is at its most favorable. But there is an additional reason why MIRI was not merely the best tool for this observation. It was the only tool. Earth's atmosphere is saturated with water vapor that absorbs mid-infrared light at 15 microns. Ground-based telescopes are effectively blind at this wavelength. Previous space telescopes like Spitzer lacked the angular resolution and coronagraphic capability to attempt this observation. JWST is the first and currently only observatory that makes this measurement even theoretically possible. And JWST's MIRI instrument, operating above the atmosphere at cryogenic temperatures, is the only facility in existence that can exploit this window. Ground-based telescopes are blocked by atmospheric water vapor at 15 microns. Previous space telescopes like Spitzer lacked the angular resolution and coronagraphic capability to attempt this observation. JWST is the first and currently only observatory that makes this measurement even theoretically possible. This is why the August 2024 detection was so electrifying. Not because it was the first time anyone had thought to look. People have been looking for decades, but because it was the first time the right instrument existed to have a genuine chance of succeeding. JWST's MIRI coronagraph, operating at 15.5 microns, with its 4-quadrant phase mask achieving an inner working angle of roughly half an arcsecond, backed by reference differential imaging to suppress residual starlight, was the precise combination of capabilities needed to peer into the habitable zone of Alpha Centauri A. No previous telescope had all of these attributes simultaneously. The detection of S1 was not a lucky accident. It was the inevitable result of a 40-year campaign by the exoplanet community to build the tools necessary for this exact observation. The gravitational dynamics of the binary system also shape the question of what kind of planets can exist around Alpha Centauri A at all. When two stars orbit each other, their combined gravitational influence creates regions of stability and instability for any third body, like a planet. Close to either star, the gravity of that star dominates, and planetary orbits can be stable. Far from both stars, the gravitational influence averages out, and orbits can again be stable. But in between, in the chaotic zone where the gravitational pulls of both stars compete, orbits become unstable. A planet placed in this zone would be gravitationally perturbed until it was either flung out of the system entirely or sent spiraling into one of the stars. For the Alpha Centauri AB binary, numerical simulations show that stable planetary orbits around Alpha Centauri A are possible out to roughly 3 astronomical units from the star. Beyond that, the gravitational influence of Alpha Centauri B begins to destabilize orbits, especially during the binary's closest approaches when the two stars are only 11 astronomical units apart. This means the habitable zone of Alpha Centauri A, which extends from roughly 1.2 to about 2 astronomical units given the star's luminosity, sits comfortably within the region of gravitational stability. A planet can survive there, but a planet on an eccentric orbit that swings out to 3 astronomical units or beyond would be at risk of gravitational disruption over the long timescales of the system's 4.85 billion year lifetime. The candidate planet's estimated orbit, with a semi-major axis that carries it between 1 and 2 astronomical units and an eccentricity of around 0.4, falls within the stable zone. The team's orbital simulations explicitly tested for gravitational stability in the presence of Alpha Centauri B and retained only those orbits that survived over long timescales. This is reassuring. It means the planet, if real, is not in a dynamically forbidden zone. It is in a place where physics allows it to exist. But the very fact that a Saturn-mass gas giant could exist in this environment raises profound questions about planetary formation. The standard model of giant planet formation, called core accretion, holds that gas giants form by first assembling a solid core of roughly 10 Earth masses from dust and ice in the protoplanetary disk, and then accreting a massive gaseous envelope from the surrounding nebula before the gas dissipates. This process takes several million years and requires a calm, well-ordered disk with enough material at the right distance from the star. A binary companion, like Alpha Centauri B, would gravitationally truncate the protoplanetary disk around Alpha Centauri A, limiting its outer extent to roughly 2 to 3 astronomical units. This truncation reduces the total mass available for planet formation and stirs up the disk dynamically, making it harder for solid cores to grow through gentle collisions. The existence of a Saturn-mass gas giant at 1 to 2 astronomical units in this environment would challenge the simplest versions of the core accretion model. It would suggest either that the disk was more massive or more efficient at forming planets than expected, or that the planet formed farther out and migrated inward, or that some alternative formation mechanism such as gravitational instability, where a massive disk fragment collapses directly into a giant planet, played a role. Each of these possibilities would reshape our understanding of how planetary systems form in binary environments, which is significant because roughly half of all Sun-like stars in the galaxy are in binary or multiple star systems. If giant planets can form and survive in the Alpha Centauri system, they can probably form and survive in many similar binaries throughout the galaxy. And there is one final, tantalizing implication. The candidate planet is a gas giant. It cannot itself support life as we understand it. You are not going to find forests or oceans on the surface of a Saturn-mass ball of hydrogen and helium. But gas giants in our own solar system have something that dramatically changes the equation. Moons. Saturn alone has over 270 known moons. Jupiter has 95. Some of these moons, like Europa and Enceladus, possess subsurface oceans of liquid water beneath their icy crusts, heated by tidal forces from their parent planets. They are considered among the most promising places to search for life in our own solar system. If the Alpha Centauri A planet candidate is real, and if it possesses a system of large moons, those moons would orbit within the habitable zone of a sun-like star. They would receive roughly the same level of stellar radiation as Earth. They could potentially have atmospheres, magnetic fields, geological activity, and liquid water. They would be the closest potentially habitable worlds orbiting a sun-like star, closer and more accessible than any other target in the galaxy. The detection of such moons is far beyond current technology, but the mere possibility, resting on the foundation of a single faint infrared detection, is enough to justify every hour of telescope time that has been spent and every hour that will be spent trying to determine whether S1 is real. This is what makes Alpha Centauri a uniquely important and uniquely maddening. It is the nearest sun-like star. It is the most scientifically valuable target for exoplanet characterization. It is surrounded by the most favorable conditions for hosting a habitable world. And it is wrapped in a fortress of blinding starlight, binary contamination, and observational difficulty that has defeated every attempt to breach it for over 30 years. The James Webb Space Telescope is the first instrument powerful enough and precise enough to have a genuine chance. And in August of 2024, it delivered the first credible evidence that something is hiding in the glare. Whether that something is a planet, a wisp of dust, or an artifact of the telescope's own optics remains to be determined. But the target has never been more important, and the tool has never been sharper. The stage is set for the most consequential observation in the history of direct imaging. All that remains is the light. There is a number that defines the entire history of exoplanet science. Over 6,000 and counting. That is roughly how many confirmed exoplanets have been catalogued as of today. Worlds of every conceivable size and composition. Gas giants larger than Jupiter orbiting so close to their stars that their atmospheres are being stripped away in real time. Rocky planets smaller than Earth locked in tight orbits around dim red dwarfs. Worlds made of ice. Worlds made of iron. Worlds with no star at all, drifting through the interstellar void like cosmic orphans. In just 3 decades, we have gone from knowing of exactly 0 planets outside our solar system to knowing of thousands. It is one of the great scientific revolutions of the modern era. But here is the part that almost nobody talks about. Of those 6,000 confirmed worlds, the overwhelming majority have never been seen. Not directly, not as points of light in an image, not as actual photons collected from the surface or atmosphere of the planet itself. They are inferred. They are shadows and wobbles and timing variations. They are absences of light and mathematical signatures extracted from the data of their parent stars. The planet is real, but what the telescope actually recorded was the behavior of the star, not the planet. The planet is a ghost that makes the star dance. The transit method, responsible for the largest share of confirmed discoveries thanks to NASA's Kepler mission and its successor TESS, works by watching a star's brightness over time. When a planet crosses the face of its star as seen from Earth, it blocks a tiny fraction of the starlight, causing a measurable dip in the light curve. For a Jupiter-sized planet crossing a sun-like star, the dimming is roughly 1%. For an Earth-sized planet, it is roughly 0.01%. Kepler stared at a single patch of sky for 4 years, monitoring over 150,000 stars simultaneously, waiting for these periodic dips. It found thousands of them, but it never saw the planets. It saw their shadows. The radial velocity method, the technique that produced the first confirmed exoplanet around a sun-like star in 1995, works by measuring the Doppler shift in a star's spectral lines caused by the gravitational tug of an orbiting planet. As the planet orbits, it pulls the star slightly toward and away from the observer, causing the wavelengths of the star's light to shift back and forth by a tiny amount. A Jupiter-mass planet at 1 astronomical unit causes a radial velocity variation of roughly 12 meters per second. An Earth-mass planet at the same distance would cause a shift of roughly 9 centimeters per second, a value so small that measuring it requires spectrographs of almost unimaginable precision. But again, what the telescope measures is the motion of the star. The planet is inferred from the star's behavior. It is a deduction, not an observation. These indirect methods have been spectacularly successful. They have revealed the demographics of planetary systems across the galaxy. They have shown us that planets are common, that most stars host at least one planet, and that the diversity of planetary systems far exceeds anything we imagined based on our own solar system. But they have fundamental limitations. The transit method only works when the planet's orbit happens to be aligned edge-on from our perspective, which for habitable zone planets around Sun-like stars occurs less than 1% of the time. The radial velocity method tells you the planet's minimum mass and its orbital period, but it cannot tell you what the planet looks like, what its atmosphere is made of, or whether it is a barren rock or a living world. To answer those questions, you need to do something far more difficult. You need to actually see the planet. You need to catch photons that left the planet's surface or atmosphere and traveled across the void to your detector. You need direct imaging. Direct imaging is the youngest and most technically demanding of the major exoplanet detection methods. It is also the most powerful. If you can isolate the light from a planet, you can spread that light into a spectrum and read its chemical composition like a fingerprint. You can identify molecules in the atmosphere, water vapor, methane, carbon dioxide, ozone. You can measure the planet's temperature. You can potentially detect signs of biological activity. You can study the planet as a world, not as a statistical shadow. But the difficulty of direct imaging is staggering. Consider the basic problem. A sun-like star shines with a luminosity of roughly 3.8 times 10 to the power of 26 watts. A Jupiter-like planet in reflected visible light is roughly 1 billion times fainter. Even in the thermal mid-infrared, where the contrast is most favorable for cool planets, the star outshines the planet by a factor of 10,000 or more. And the planet sits right next to the star, separated by an angular distance so small that from any reasonable distance, the two sources blend into a single point of light in the telescope's image. The starlight does not just outshine the planet, it actively drowns it, flooding the detector with photons that scatter and diffract into the exact region of the image where the planet should be. We have already seen how the coronagraph suppresses starlight, but suppression is not elimination. Even after the 4-quadrant phase mask and the Lyot stop have done their work, residual starlight leaks through and forms a complex pattern of speckles and rings across the image. These speckles are determined by imperfections in the telescope's optics, the alignment of the coronagraphic mask, and the thermal and mechanical stability of the entire system. They are the enemy. They can mimic the appearance of a planet. They can hide a real planet beneath their noise, and they shift and evolve over time as the telescope breathes thermally and vibrates mechanically. This is where the reference star subtraction we discussed earlier encounters its limits. The reference star is never a perfect match for the target. The telescope's optical state is never precisely identical between two observations, separated by hours or days. Small mismatches leave behind subtraction residuals, bright and dark blotches in the final image that can masquerade as companions or swallow real ones. The art of direct imaging lies in minimizing these residuals and distinguishing real signals from their ghosts. For the Alpha Centauri observations, the binary contamination we have discussed throughout this story pushed this challenge to an extreme. The team was effectively performing coronagraphy on 2 stars simultaneously, a level of data reduction complexity unlike almost any other coronagraphic observation in JWST's history. The team reinforced this approach with the telescope roll strategy introduced during the August observations, rotating JWST between exposures so that real sources shifted on the detector while instrumental artifacts stayed fixed. For the August 2024 campaign, the execution was successful. The pipeline recovered S1 consistently across the different rolls, increasing confidence that it was a real source rather than a fixed instrumental artifact. But as we discussed earlier, the February 2025 follow-up suffered a setback. For Alpha Centauri A, the planned observation in August of 2024 included multiple roll angles, and the execution was successful. The pipeline recovered S1 consistently across the different rolls, increasing confidence that it was a real source rather than a fixed instrumental artifact. But as we discussed earlier, the February 2025 follow-up suffered a setback. Only one of the two planned rolls was successfully executed, cutting the team's ability to perform angular differential imaging in half. Combined with the 10 milliarcsecond positional mismatch in the reference star subtraction, the February data were significantly less sensitive than the August data. This is a sobering reminder of how fragile these observations are. Everything must go right. The telescope must point perfectly. The coronagraph must be aligned precisely. The reference star must be observed under identical conditions. The rolls must execute successfully. A failure in any single link of this chain degrades the entire result. The April 2025 observations achieved better execution, but the planet was still not detected. Whether this reflects the planet's orbital position, the intrinsic limits of the observation, or the absence of a real planet remains an open question. The team set upper limits on what could have been detected, constraints on the brightness of any object at various separations from the star, and those limits inform future observation planning. It is worth placing the Alpha Centauri observation in the broader context of what JWST has achieved with direct imaging. The telescope has already demonstrated remarkable coronagraphic capabilities. In its first year of science operations, JWST used its near-infrared camera, NIRC-CAM, to directly image the exoplanet HIP 65426b, a young super-Jupiter orbiting a Sun-like star at a separation of roughly 90 astronomical units. That observation was a dramatic proof of concept, but the target was relatively easy by direct imaging standards. The planet was young, hot, and far from its star, making it bright in the near-infrared and well separated from the stellar glare. MIRI's coronagraph has been used to image the 4 planets of the HR 8799 system at mid-infrared wavelengths for the first time, providing photometric data points that constrained the planet's atmospheric properties and revealed a warm inner debris disk. These observations were groundbreaking, but again, the HR 8799 planets orbit at separations of 15 to 70 astronomical units from a young A-type star. The contrast ratios and angular separations were far more favorable than what the Alpha Centauri observation demanded. In June of 2025, a team led by Anne-Marie Lagrange announced the discovery of TWA 7b, a previously unknown exoplanet directly imaged by MIRI's coronagraph around a young M-type star in the TW Hydrae Association. This was the first exoplanet discovered entirely through JWST direct imaging, as opposed to follow-up imaging of a previously known planet. It demonstrated that MIRI's coronagraph could not only characterize known planets, but find new ones. The result was published in Nature and was widely celebrated as a milestone. But the Alpha Centauri A observation is in a different league entirely. The candidate planet is not orbiting a young star. It is orbiting a mature 4.85 billion-year-old solar twin. It is not far from its star at tens or hundreds of astronomical units. It is at 1 to 2 astronomical units, right at the inner working angle of the coronagraph. It is not a hot young giant blazing in the near-infrared. It is a cool, old, Saturn temperature world emitting faintly in the thermal mid-infrared. The contrast ratio is worse, the angular separation is smaller, the planet is dimmer, and the binary companion adds a layer of complexity that does not exist for any other direct imaging target. The Alpha Centauri observation is JWST operating at its absolute ceiling. It is the telescope doing something it was not specifically designed to do, pushed there by the ingenuity of the science team and the unique importance of the target. This raises a natural question. If JWST is already at its limits, what comes next? What tools are being built or planned that could confirm the Alpha Centauri candidate, or push the search for nearby exoplanets even further? The most immediate next step is the Nancy Grace Roman Space Telescope, NASA's next flagship astrophysics mission, currently scheduled for launch as early as late 2026 or 2027. Roman is a very different telescope from JWST. Its primary mirror is 2.4 meters in diameter, significantly smaller than JWST's 6.5 meter primary, which means it collects far fewer photons per unit time. It does not observe in the thermal mid-infrared. Its instruments are optimized for the visible and near-infrared, wavelengths where the contrast between a sun-like star and a cool planet is far more extreme than at 15 microns. But Roman has one critical advantage. It carries a dedicated coronagraph instrument that represents a generational leap in technology. The Roman coronagraph is the first space-based instrument to incorporate active wavefront control, a technique where deformable mirrors within the instrument continuously adjust their shape in real time to correct for optical imperfections and minimize the residual starlight speckles that plague conventional coronagraphs. On JWST, the coronagraphic speckle pattern is essentially fixed by the telescope's optics. You can subtract it using reference star observations, but you cannot actively control it. On Roman, the deformable mirrors will actively sculpt a dark hole in the image around the star, a region of suppressed starlight, where planets can be detected at contrasts of roughly 100 million to 1 in reflected visible light. This is orders of magnitude better than what any existing coronagraph can achieve. The Roman coronagraph was designed as a technology demonstration, a proof of concept for the wavefront control techniques that will be needed by future missions. But it is also a real scientific instrument with real observing capabilities. If pointed at Alpha Centauri A, it could potentially detect the reflected visible light from a giant planet in the habitable zone, providing an independent confirmation of the MIRI detection through a completely different observational technique at a completely different wavelength. Seeing the same planet in both thermal mid-infrared emission and reflected visible light would be extraordinarily powerful. The two measurements would constrain different physical properties. The mid-infrared tells you about the planet's temperature and thermal structure. The visible light tells you about its reflectivity, cloud properties, and atmospheric composition. Together, they would paint a portrait of the planet far richer than either observation alone. Beyond Roman, the astronomical community is planning even more ambitious facilities. The Habitable Worlds Observatory, a mission concept currently under development as NASA's next great observatory after Roman, would be designed from the ground up to directly image and characterize Earth-like planets around nearby sun-like stars. It would carry a coronagraph capable of achieving contrasts of 10 billion to 1, sufficient to detect a pale blue dot, an Earth twin, orbiting a star like Alpha Centauri A. The Habitable Worlds Observatory would not just find planets. It would analyze their atmospheres, searching for biosignatures, chemical combinations like oxygen and methane that are difficult to produce without biological activity. It would, for the first time, give us the ability to search for evidence of life on specific nearby worlds. But the Habitable Worlds Observatory is decades away. Its design is still being refined. Its launch is not expected until the late 2030s or early 2040s. In the meantime, the community must work with the tools it has, and those tools, principally JWST and soon Roman, are being pushed harder and further than their designers ever anticipated. Ground-based telescopes are also advancing rapidly. The European Extremely Large Telescope, currently under construction in Chile's Atacama Desert, with a primary mirror 39 meters in diameter, will carry an instrument called METIS, the Mid-Infrared ELT Imager and Spectrograph. METIS will observe at wavelengths from 3 to 13 microns, slightly shorter than MIRI's 15-micron sweet spot, but with an angular resolution roughly 6 times better than JWST's due to the vastly larger primary mirror. METIS could potentially resolve planets at smaller angular separations from their stars than JWST can, and its spectroscopic capabilities would allow chemical characterization of any detected atmosphere. However, ground-based mid-infrared observations still face the fundamental challenge of atmospheric absorption. At wavelengths beyond about 13 microns, the atmosphere is largely opaque. METIS will push the boundaries of what is possible from the ground, but it cannot fully replicate what MIRI does from the vacuum of space. The combination of all these facilities, JWST in the mid-infrared from space, Roman in the visible from space, the ELT from the ground in the near and mid-infrared, creates a web of complementary capabilities that did not exist even 5 years ago. Each telescope sees the universe through a different lens, at different wavelengths, with different strengths and limitations. A planet that is invisible to one might be detectable by another. A measurement that is ambiguous from one observatory might be clarified by data from a second. The Alpha Centauri, a planet candidate, if it is real, will eventually be caught in this web. It cannot hide from all of them at the same time. But here is the deeper truth that the Alpha Centauri observation reveals about the state of exoplanet science. We are at an inflection point. For the first 30 years of the exoplanet era, discovery was the game, finding planets, counting them, cataloging their sizes and orbits, building a census. That era is not over, but it is maturing. The frontier is shifting from discovery to characterization, from knowing that a planet exists to understanding what it is. What is its atmosphere made of? Does it have clouds? Does it have weather? Does it have water? Does it have the chemical signatures of life? Direct imaging is the gateway to that frontier. It is the only technique that isolates the planet's own light, allowing spectroscopic analysis of its atmosphere. Every other detection method tells you about the planet's shadow or its gravitational influence. Direct imaging tells you about the planet itself. And the Alpha Centauri A candidate, sitting in the habitable zone of the nearest solar twin, would be the single most important target for this new era of characterization. Not because it is the most exotic or the most extreme, but because it is the most accessible. It is the one planet, if it exists, that we could study most deeply with the tools we have and the tools we are building. This is why the February and April non-detections, while disappointing, do not diminish the importance of the effort. Even the non-detections carry scientific value. The upper limits set by the follow-up observations constrain the brightness and therefore the size and temperature of any planet that could be present at various separations from the star. They inform the orbital models. They tell future observers exactly how deep they need to go to confirm or rule out the candidate. Emily Rickman, a European Space Agency astronomer at the Space Telescope Science Institute who was not involved in the research, put it precisely. All data, whether it is a detection or not, tells you something, she said. Even if this ultimately is a non-detection and the planet candidate is something else, I think it is a really important paper in understanding the true capabilities that JWST's MIRI can push to. That last point deserves emphasis. The Alpha Centauri A observation is not just a planet search. It is a stress test of the most advanced astronomical instrumentation ever built. It pushes MIRI's coronagraph to its smallest working angles, its faintest contrast levels, its most complex observing scenarios. Every challenge the team encountered, the binary contamination, the target acquisition difficulties, the reference star mismatches, the compromised role in February provides data that will improve future observations. The techniques developed for this campaign, the blind offset acquisition using Epsilon Muscae, the dual star PSF subtraction, the orbital constraint modeling combining detections and non-detections, these are innovations that will be applied to every subsequent high-contrast observation JWST performs. The Alpha Centauri campaign is building the playbook for a generation of astronomers who will use these tools to search for and characterize planets around dozens of nearby stars. And so the technological story of this detection is not a story of a single observation that succeeded or failed. It is a story of an entire field reaching the threshold of a capability that it has been chasing for decades. The ability to directly detect cool, mature planets in the habitable zones of nearby sun-like stars. JWST has demonstrated that this threshold can be touched. The Alpha Centauri, a candidate, is the first handprint on that threshold. Whether it is a planet or a phantom, the fact that the observation was even possible represents a turning point in how we study other worlds. The instruments exist. The techniques are being refined. The targets are identified. The next generation of telescopes will push through the threshold entirely. And when they do, the data they return will reshape our understanding of planetary systems, habitability, and our place in the galaxy. The question is no longer whether we can see planets around nearby stars, it is what we will find when we look closely enough. And the answer to that question might already be orbiting Alpha Centauri, circling quietly in the dark, waiting to emerge from behind the glare of its star one more time. Let us return to where this story began. A team of astronomers pointed JWST at the nearest sun-like star in the cosmos. They blocked the star's light with a mask smaller than a fingernail. And in the darkness that remained, they found a faint thermal glow consistent with a Saturn-mass planet orbiting in the habitable zone. They tried to explain it away. They could not. They looked again. The signal was gone. They looked a third time. And now, as of this moment, the planet candidate exists in a kind of scientific purgatory, suspended between discovery and dismissal, defined not by what we know, but by the precise shape of what we do not know. This is not a comfortable place for the human mind to sit. We want answers. We want the story to end with either a triumphant confirmation or a clean retraction. We want the planet to be real and spectacular, or we want it to be debunked and forgotten. We do not want ambiguity. We do not want the phrase, "further observations are needed." But that phrase, tedious as it sounds, is the honest truth of where this story stands. And the fact that it stands there, balanced on the knife edge between real and not real, tells us something profound. Not just about this particular planet candidate, but about the nature of astronomical observation itself and the extraordinary difficulty of knowing anything about the universe with certainty. Consider what the team was attempting. They were trying to detect an object over 10,000 times fainter than the star it orbits, at an angular separation so small that it sits right at the boundary of the telescope's ability to suppress starlight, around a target so bright that it saturates most instruments, and so entangled with a binary companion that every image is contaminated by scattered photons from a second star. They were trying to do this from a telescope floating 1.5 million kilometers from Earth, communicating through the deep space network, using a coronagraphic mask designed and manufactured years before anyone knew this specific observation would be attempted, and they succeeded once. They got one clean look, one epoch of data in which the signal emerged from the noise clearly enough to survive every test the team could throw at it. Then the universe closed the window. The planet, if it exists, moved along its orbit, dipped inside the coronagraph's inner working angle, and became invisible. Not because the telescope failed, not because the team made an error, but because orbital mechanics are indifferent to human timelines. The planet does not know that we are looking. It does not care that we secured director's discretionary time. It does not adjust its trajectory to match our observation schedule. It moves according to gravity, and gravity does not negotiate. This is one of the most humbling aspects of observational astronomy. We are passive observers of a universe that operates on its own terms. We cannot pause an orbit. We cannot rewind a transit. We cannot ask a star to dim itself so we can see the planet more clearly. We can only build the best instruments we can, point them at the sky at the moments we choose, and hope that the universe is in a cooperative mood. Sometimes it is. Sometimes a planet is in the right place at the right time, and the telescope is functioning perfectly, and the data pipeline works without error, and the signal rises above the noise. Those are the moments that make headlines. But for every one of those moments, there are dozens of observations that return upper limits and non-detections and ambiguous signals that require years of follow-up to resolve. The Alpha Centauri, a candidate, is living through that process right now. And this process, as frustrating as it is exactly how science is supposed to work. The history of exoplanet discovery is not a history of clean, dramatic revelations. It is a history of hard-won, incremental, often contested progress. The first confirmed exoplanet around a sun-like star, 51 Pegasi b, was announced in October of 1995 by Michel Mayor and Didier Queloz. Their detection was based on radial velocity measurements, showing a periodic Doppler shift in the star's spectral lines. The astronomical community's initial reaction was skepticism bordering on disbelief. A Jupiter-mass planet orbiting its star in just 4.2 days, at a distance of only 0.05 astronomical units? That was impossible according to every model of planetary formation that existed at the time. Giant planets were supposed to form in the cold outer reaches of a protoplanetary disk, like Jupiter and Saturn in our own system. A hot Jupiter was a contradiction in terms, but the data held up. Other teams independently confirmed the radial velocity signal within weeks, and the field of exoplanet science was born, not from a moment of universal acclaim, but from a moment of universal confusion. The discovery did not fit the models. It forced the models to change. That is the pattern. The universe does something unexpected. Scientists argue about whether it is real. More data accumulates. The arguing intensifies. Eventually, the weight of evidence tips in one direction or the other, and the textbooks are rewritten. The Alpha Centauri, a candidate, is early in that cycle. It is at the stage where the data are suggestive but not conclusive, where the team has done everything right and the community is cautiously intrigued but not yet convinced. This is healthy. This is the immune system of science working as intended. Extraordinary claims require extraordinary evidence, and a planet orbiting in the habitable zone of the nearest sun-like star, detected by direct imaging for the first time, is about as extraordinary as claims get. What does the community need to see before the candidate can be elevated from intriguing to confirmed? The answer is straightforward in principle and agonizing in practice. They need at least one more detection, ideally two, at different orbital positions, demonstrating that the object moves in a manner consistent with a gravitationally bound Keplerian orbit around Alpha Centauri A. If JWST observes the system in August of 2026 and recovers S1 at a position consistent with the predicted orbit, that would be a massive step forward. If a second independent method, such as a radial velocity detection of the stellar wobble caused by the planet's gravitational pull, independently corroborates the orbital parameters, the case would become nearly airtight. If the Nancy Grace Roman Space Telescope, after its launch, detects the planet in reflected visible light at a position and brightness consistent with the MIRI data, the confirmation would be essentially complete. Each of these steps requires time, resources, and a measure of luck. The August 2026 JWST observation is the most immediate opportunity. The team has identified the window. They understand the orbital geometry. They know which telescope roll angles and reference star observations will maximize their sensitivity. But they still need to be awarded the telescope time. JWST is the most oversubscribed observatory in history. Competition for observing hours is ferocious. The Alpha Centauri proposal will be evaluated alongside hundreds of other scientifically compelling programs. And while the case is strong, there is no guarantee. The telescope's schedule is finite. The universe's demands on it are infinite. The radial velocity path is also challenging. As we discussed, the binary orbital motion of Alpha Centauri A and B creates enormous systematic noise in radial velocity measurements. Detecting a Saturn-mass planet at 1 to 2 astronomical units would require measuring a stellar wobble of roughly 3 to 4 meters per second against a background of binary-induced motion that varies by kilometers per second. Current spectrographs can achieve sub-meter per second precision on quiet, single stars, but achieving that precision on a bright star in a complex binary system with its own stellar activity and magnetic cycles is a different problem entirely. Several teams around the world are working on new radial velocity campaigns targeting Alpha Centauri, but a clean detection of the planetary signal is not expected to come quickly or easily. The Roman Space Telescope represents perhaps the most exciting confirmatory pathway. Its coronagraph, with active wavefront control and the ability to create a deep, dark hole in the stellar image, was designed precisely for this class of observation. If Roman can detect the planet in reflected starlight, it would provide not only positional confirmation but entirely new physical information. The visible light reflectivity of the planet, its albedo, would constrain the composition and structure of its upper atmosphere. Combined with MIRI's thermal emission data, the two measurements would yield a comprehensive picture of the planet's energy budget, how much energy it receives from its star, how much it reflects, how much it absorbs and re-emits as heat. This is the kind of multi-wavelength characterization that was pure science fiction 10 years ago. It is now technically achievable for this specific target if the planet is real. But confirmation is not the only scientifically valuable outcome. Even if the planet candidate is ultimately ruled out, if it turns out to be a subtle instrumental artifact, or a fluctuation in the zodiacal dust background, or some other astrophysical source masquerading as a planet, the effort will not have been wasted. The non-detection itself would set powerful constraints. It would tell us that there is no Saturn-mass planet in the habitable zone of Alpha Centauri, a brighter than a specific threshold. That constraint narrows the parameter space for future searches. It tells the next team exactly where the boundary lies and how much deeper they need to go. It is a stepping stone, not a dead end. And the techniques developed during this campaign have already advanced the field. The blind offset target acquisition using Epsilon Muscae, the dual-star PSF subtraction strategy for binary systems, the orbital constraint framework that combines detections and non-detections across different telescopes and epochs. These innovations will be applied to every future high-contrast imaging program on JWST and its successors. The Alpha Centauri campaign has become a case study in how to push a coronagraph to its limits, and the lessons learned will echo through the field for decades. There is a deeper philosophical point here that extends beyond the technical details. The Alpha Centauri, a candidate, forces us to confront a fundamental truth about our relationship with the cosmos. We are observers, not participants. We cannot reach Alpha Centauri, not today, not in our lifetimes. The fastest spacecraft we have ever built would take over 6,000 years to make the journey. Even the most ambitious proposed interstellar missions, like the breakthrough Starshot concept, which envisions accelerating tiny light sail probes to 20% of the speed of light using ground-based lasers, would take roughly 20 years to reach Alpha Centauri, and 4 more years for the data to travel back at the speed of light. That is a generation. And those missions exist only on paper. For the foreseeable future, everything we learn about Alpha Centauri and its potential planets will come from photons. Photons that left the star system 4.37 years ago and traveled across the void at 300,000 kilometers per second to land on a detector cooled to below 50 Kelvin on a telescope floating at the second Lagrange point. Every observation is an act of archaeology. We are studying light that is already years old by the time it reaches us. The planet we might have glimpsed in August of 2024 was not where we saw it at the moment we saw it. It was where it had been 4.37 years earlier, when the photons that carried its image began their journey. By the time we processed the data and published the papers, the planet had moved even further along its orbit. We are always looking at the past. We are always one step behind. And yet, despite this limitation, despite the vast distance and the speed of light delay and the impossibility of visiting, we have managed to build instruments precise enough to block the light of a star and detect a thermal whisper from a world 4 light years away. That is not a failure of human ambition, that is its triumph. The fact that we can even attempt this observation, let alone obtain a credible detection, is a testament to the cumulative ingenuity of thousands of engineers, scientists, and technicians who designed, built, launched, and operate the James Webb Space Telescope. It is a testament to the mathematical frameworks that allow us to model stellar point spread functions, simulate coronagraphic performance, and fit orbital parameters to sparse data. It is a testament to the culture of science itself, which demands that every claim be tested, every result be challenged, and every conclusion be held provisionally until the evidence compels otherwise. The silence from Alpha Centauri A in February and April of 2025 is not a defeat, it is a data point in an ongoing investigation. It tells us that the planet, if it exists, was not in a favorable position at those times. It tells us that the coronagraph's inner working angle is the limiting factor. It tells us that elliptical orbits create windows of visibility and windows of invisibility, and that timing is everything. The silence is not empty, it is informative, and it is temporary. The next window opens in August of 2026. The light from Alpha Centauri A will fall on Miri's detector once again. The coronagraph will suppress the glare. The pipeline will subtract the residuals, and in the shadow of the star, either a faint point of thermal light will be waiting, or it will not. If it is there, the discovery will be one of the most significant in the history of astronomy. A gas giant planet, roughly the mass of Saturn, orbiting in the habitable zone of the nearest solar twin. A world close enough to study in extraordinary detail. A world whose moons, if it has them, could harbor conditions suitable for liquid water and perhaps even life. A world that would become the primary target for every major astronomical facility built in the next 50 years. A world that would transform Alpha Centauri from a point of light in the southern sky into a place, a neighbor, a destination. If it is not there, the search will continue. Because the non-detection of a Saturn-mass planet does not mean the system is empty. It means we have not looked deeply enough, or long enough, or at the right wavelength. Smaller planets, rocky worlds, Earth-mass bodies in tighter orbits, these would be below the current detection threshold of Miri's coronagraph. They could be there. They could be orbiting quietly in the habitable zone, too small and too cold for our current instruments to see, but waiting for the next generation of telescopes to reveal them. The Habitable Worlds Observatory, if built, would have the sensitivity to detect an Earth twin around Alpha Centauri A. That mission is decades away, but the foundation for it is being laid right now, in part by the very observations we have been discussing. This is the nature of exploration at the frontier. You do not get clean answers on the first try. You get hints and constraints and tantalizing possibilities. You get a single detection followed by 2 non-detections, and a set of orbital models that say the disappearance is consistent with the planet being real. You get a scientific community that is excited and cautious in equal measure. You get a timeline measured not in days or weeks, but in years and decades. And you get the slow, grinding, magnificent accumulation of evidence that eventually, after all the arguments and all the reanalyses and all the follow-up campaigns, converges on something true. We do not yet know whether Alpha Centauri A has a planet. We know that JWST saw something in August of 2024 that looked like one. We know that the same something, or something very much like it, was glimpsed by the Very Large Telescope in 2019. We know that both detections are consistent with a single object on a stable elliptical orbit. We know that the non-detections in early 2025 are explained by orbital geometry. We know that the next favorable observation window is August of 2026. And we know that if the planet is confirmed, it will be the closest world ever found orbiting in the habitable zone of a sun-like star. What we do not know is whether the universe will cooperate, whether the photons will arrange themselves in the right pattern on the right detector at the right time to push the evidence over the threshold of confirmation. That is not in our control. All we can do is build the best instruments, design the best observations, analyze the data with the most rigorous methods, and keep looking. And that is exactly what the team intends to do. Beichmann and Sanghi and their collaborators are preparing for August of 2026. They are refining their orbital models. They are optimizing their observation strategy. They are planning the reference star observations and the telescope roll angles and the data reduction pipeline. They are doing everything within human power to be ready for the moment when JWST turns its gaze once more toward the closest sun-like star and asks, in the language of infrared photons, the oldest question our species has ever asked. Is anyone there? The star will not answer in words. It will answer in data, in photon counts and noise statistics and PSF subtractions. In the presence or absence of a faint thermal glow at a specific angular separation, at a specific wavelength, at a specific moment in a specific orbit. And that answer, whatever it is, will be written not in the bold, declarative sentences of a headline, but in the cautious, conditional language of a scientific paper. We detect a point source consistent with, or we set an upper limit on the brightness of, the prose will be dry. The implications will be anything but. Because behind the dry prose is a question that keeps us awake at night. A question that has driven every telescope ever built, every mission ever launched, every hour of observation ever logged. The question is not really about a planet. It is about us. It is about whether the conditions that gave rise to life on Earth are unique to this one unremarkable rock orbiting this one unremarkable star, or whether those conditions are replicated in some form around the star next door, the Alpha Centauri. A planet candidate does not answer that question, not yet, but it sharpens it. It takes a question that was abstract and makes it concrete. It takes a search that was theoretical and makes it observational. It takes a dream and gives it coordinates. 4.37 light-years away, 1 to 2 astronomical units from the star, a Saturn-mass body on an elliptical orbit, visible in the thermal mid-infrared at 15.5 microns. Detectable by a 4-quadrant phase mask coronagraph on the mid-infrared instrument of the James Webb Space Telescope when the orbital geometry is favorable and the observation is executed flawlessly and the data reduction reveals what the raw images hide. That is where the story stands, not at the end, not at the beginning, but at the moment of maximum uncertainty, which is also, if you think about it, the moment of maximum possibility. The planet might be there, it might not. We will find out. Not today, not tomorrow, but soon. By By the standards of a universe that has been waiting 4.85 billion years for someone to ask the question, the telescope is ready. The team is ready. The orbit will bring the planet, if it exists, back into view. And when it does, the most powerful eye humanity has ever built will be watching. It will be staring into the shadow of our nearest stellar neighbor, searching for the faintest trace of a world that might just be the closest thing to home we have ever found outside our own solar system. The glare of the star will fight back, as it always does. The noise will rage, as it always does. But somewhere in that noise, at the edge of what is detectable, the answer is waiting. It has always been waiting. We are only now building the instruments sensitive enough to hear it. And if there is a planet orbiting Alpha Centauri A, circling quietly in the habitable zone of a star almost identical to our own sun, it does not know we are looking. It does not know that a species on a small rocky world 4 light-years away has spent decades building machines to find it. It does not know that its thermal glow, a faint exhale of infrared light escaping into the void, was captured for a single brief moment by a gold-plated mirror floating in the darkness at the edge of the Earth's gravitational influence. It does not know any of this, but we do. And that is the difference between a universe that is merely vast and a universe that is known. We are the ones who look. We are the ones who ask. And we will keep asking until the darkness answers.